Hello, everybody, and welcome back to Creation Myths. Today, we have an actual creation myth to talk about. We are going to cover the creation myth that protein orchards destroy evolution. That's today's topic. So here is what you need to know about protein orchards. The background here is that cellular life has universal common ancestry. Like all cellular organisms are descended from a last universal common ancestor population of cellular organisms. That is not the case for all proteins or all genes. Genes do not all share common ancestry. Instead, we have this thing called gene families, right? And gene families refer to groups of genes that share common ancestry. And it is the case that there are many gene families among cellular organisms. That's just a fact about living things. There are many, many gene families, and those gene families have distinct, separate evolutionary origins from each other. So it is not the case that all protein coding genes share common ancestry, right? We call those distinct groups that evolved independently gene families. Now, some creationists, and one creationist in particular, call this a protein orchard, and this is based on the creationist concept of an orchard of life, in contrast to the evolutionary tree of life that you hear about. Now, in the tree of life concept, the idea is that all cellular life shares a common ancestor, so it looks like a tree with a single trunk, and then things branch off of it. But in the orchard of life, you don't have one tree, you have many trees where each individual tree represents a separate created kind. And you can look at the figure right here from Answers in Genesis to have kind of an idea of what we mean by this. So here you've got your lizard kind and your frog kind and your dinosaur kind, and they're extinct, and your bird kind and your ape kind and your dog kind. And they don't share common ancestry. They have separate origins. So this is called the orchard of life. And one creationist in particular applies this concept to gene families and calls that a protein orchard, where each protein or each group of proteins has an independent history and they were separately created. The source on this is really one specific creationist. If you hear this argument about protein orchards, you're going to hear it from Sal Cordova. Now, Sal Cordova is a young Earth creationist. He's been on my channel a bunch. I've been on his channel a bunch. We go way back talking about this stuff. He was kind of a significant name in the intelligent design movement in the early 2000s, and now he is a relatively prominent young Earth creationist. You can find him on YouTube. I'll link his channel down below. He gave a recent conference talk on this topic, recent as of mid-2024. I went back and looked. I couldn't find what conference it was or what the talk was called or when it was or anything, but I know it was relatively recent as I record this. So I apologize for not having all that information. Sal, sorry, I forget the conference, but if anybody remembers, wants to tell me, please let me know. He also did an interview on this topic with on the Real Science radio show that aired on May 9th, 2024, and I actually had him on this channel, and we talked about this topic on May 15th, 2024, and both of those are linked down below if you want to watch them. So here is the claim related to protein orchards. Protein/genes do not all share common ancestry, which is true. So new proteins must evolve for evolution to be true, which is also the case. Yes, everybody agrees on that. Now, however, what creationists will then argue is that new proteins/genes are sufficiently improbable that this would require statistical miracles. Therefore, evolution via undirected processes is false. And so that's kind of a summary of this argument, and I'm actually going to show you Sal making this argument just so you can hear it in his own words. So listen to this, then we'll come back and talk about it.
I don't think there is a universal common ancestor for all proteins. And I was in a recent debate with a secular Satanist, Aaron Ra. He finally conceded to me there's no common ancestor for all proteins/genes.
Wait a minute. The Satanist conceded something?
Yeah, the Satanist was defeated. I mean, I don't think he realized evolutionary theory has just been defeated. So let's just assume that all organisms descended from a universal common ancestor. The point about the parts, though, is they don't descend from a universal ancestral part, and I'll illustrate that. So the thing is, for universal common ancestry to be true, you would need miracles along the way to manufacture all these new parts. Because if you're evolving a bacteria to a human being, you have to create new parts.
Well, and so can I ask Sal again from the perspective of a layman? Does the impossibility of a universal common ancestor for proteins, does that defeat the idea of a universal common ancestor for creatures?
No, not immediately. And that's a very good question. It defeats it in the sense that if you say that universal common ancestor for all creatures doesn't require miracles, I just proved it needs miracles.
Now, this sounds like a new argument. This sounds like an argument that other creationists are not making. But this is actually just a new way to spin a very familiar argument, as we will see. So let's dig into this argument about protein orchards and the implications they have for the viability of evolutionary theory. There are a bunch of reasons why this argument is wrong. The first is that de novo genes are extremely common. There are many examples of de novo genes. So I'm just going to show you some papers right here. We've got hominoid-specific de novo protein coding genes, de novo origins of protein coding genes in rodents. Another example in yeast, that's fungi. Another example in rice. This is a very common thing that we've documented in various groups of plants. These 4 papers are a small sampling of what we know about how de novo genes form and examples and how frequent they are. Now, an important thing that I want to point out here is within these examples, we have examples of de novo genes, many of which exist in a single species. And the word you hear for these is often orphan genes, so it's genes that are restricted to a single lineage, often just one species. These genes exist within groups that share common ancestry according to creationists. So we should all agree that de novo genes can evolve, or creationists have to acknowledge that created kinds, the groups that are created independently, must approximate species rather than families. In general, when creationists talk about created kinds, they use that to refer approximately to the family level within the Linnaean hierarchy. But if we're using orphan genes or de novo genes and say these genes cannot evolve without some kind of intelligent input or some creative input, because these genes tend to be restricted to single species, we cannot have kinds existing at the family level. The presence of orphan genes within specific species means that those specific species must necessarily have been created separately. Now, almost no creationists think that's the case. Most creationists now reject the concept of species fixity, that species were created independently. It also makes things like the flood and the ark completely unworkable, but that's a whole separate video. So we should agree, based on the distribution of orphan genes, that these genes can actually evolve, right? De novo genes are common, and creationists should be able to agree with mainstream biologists that these things can evolve, right? So that's the first thing. De novo genes are very common, and it's actually very easy for them to evolve. I've talked about this in a separate video. The mechanism of the evolution of de novo genes is extremely well understood. I actually covered this way back in 2020, in the early days of this channel. So this video on screen right here is linked down below. If you want more details in that video, I went through a couple of papers, showed some figures where we've documented in significant detail the evolutionary history of de novo genes and the mechanisms through which non-protein coding sequences in the genome can become protein coding genes. So again, I want to emphasize this process is actually really easy. It's not a rare process, and it's not a poorly understood process. So that's that. You don't actually need miracles to get de novo genes. How do we know that? Because we've extensively documented the evolution of de novo genes, not just identifying those genes, but figuring out the pathways through which they evolve. So Sal's argument doesn't work. But that's only the first level of wrong. There are more things that we are going to talk about. The second problem with this argument is that there's no quantification. When I had this conversation with Sal, it kind of goes like this. Say, okay, well, some new genes can evolve, sure, but statistical miracles are still required for large-scale evolution. Okay, if that's the case, what's the threshold? How complex is too complex to evolve? And the answer is that we don't know. We don't have an answer. And the problem here is that without quantification, this concept is useless as an anti-evolution argument. You need to have a line in the sand where you can say, if you meet this threshold, evolutionary processes can't get the job done. Can we document that threshold? Can we identify that threshold and then show experimental support for the existence of that threshold? The answer is no, we cannot. And I asked Sal directly about this. Take a look. The question is what you talked about, the level of complexity. So here's where I get on my high horse. What's the threshold and how can we measure it? How can we quantify the complexity and then say, here's the threshold that can evolve. If you exceed that amount of complexity, you need some kind of intelligent input in order for that thing to have evolved. Where is that line and how do we know
No, those are, by the way, if I may give you a bravo for what you just said, I actually didn't even study much of the antifreeze gene. There's so much literature on both sides. I've not been able to survey it. I will point out that when you do a gene duplication or even whole genome, you're still talking about homologous genes.
Mm-hmm.
I'm wanting non-homologous.
I got you. Yes.
Okay.
Yep.
So as far as the threshold, so I'm not, this is intuitive. So you ask a pointed question, how much is enough? For me, like 10 to the 500th power, something on that order. We could throw out numbers, but it's like, well, then those numbers are based on, how good are your assumptions. And at that point, it's still, you could take that down. It's still kind of intuitive, but, so I'd say at a personal level, how improbable is it for each person to say this probably isn't, this is astronomically far from normal expectation. So when I started to examine that, I was just like, well, this is remote. I haven't. Okay, so can you take this down? I wanted to answer I'm trying to answer your question directly. John Sanford, just before one of the projects he assigned, but we never got to it. He said, why don't you take the zinc finger problem, estimate the odds, put it in a waiting time problem. And I said, well, I'm moving on to other things. And so the question you posed, it's still an outstanding problem. I'm just saying from an intuitive level, I don't have an answer. It may not satisfy you. It has satisfied others kind of at a personal level. And so I think the question you asked is very pointed. It's worth trying to address. And I don't have a number to give you. What is the threshold? I can just give it from an intuitive level. And then that particular paper kind of also articulated kind of what I was seeing. This is, when we're actually trying to make substantially complex systems, it's like, why does it seem at odds?
So if I understand you then, because my question was, how do we quantify this threshold? Where's the line? How do we know? And the answer is, we can't yet quantify it. We can't assign a specific threshold, but you can intuit that certain things are too complicated to have evolved through undirected processes because they have a bunch of different components that need to be quite precise, and they all need to operate together. You said critical things need to be there simultaneously was the phrase I wrote down as you were talking. and that is sufficiently improbable that for you and for some other people, you say, okay, that's too much for me. I don't think this could evolve through undirected processes. Is that a fair representation of kind of summary of what you just said?
Yes. And I
Okay.
just want to say, okay, if people believe in a multiverse, it's like it still could be evolved by undirected process. It just still be far from the normal expectation. Just, I'm trying to
Okay.
avoid metaphysical language because I
Yeah, I
don't
don't.
like going. But I mean,
Well,
I have tried to go through the numbers myself, kind of back of the envelope. I wouldn't present it in a peer-reviewed paper at this stage.
so again, we don't have the ability to quantify this idea. It's an intuitive thing, right? We can intuit that certain things are too complex to have evolved, but we can't quantify it. We don't have data to support that notion. That makes this concept useless. The final reason, and I think the most important reason why this argument is wrong, is that at its heart, it's just irreducible complexity. Now, irreducible complexity comes from Michael Behe and his 1996 book, Darwin's Black Box. In that book, this is paraphrasing, but he defines irreducible complexity as a system where you have well-matched interacting parts, wherein removing any one of those parts causes the system to lose its function. If you check those boxes, that system is irreducibly complex. Now, Sal does not like to use this argument. He does not like to use the term irreducibly complex when he makes creationist arguments. So instead, in that interview I mentioned earlier, he uses the term all or nothing core to describe like the required components of a specific type of protein to function. So take a look at these clips and you'll see just how similar his argument is to irreducible complexity. Take a listen.
If you have a half-formed topoisomerase and all it does is cut, that's going to be really bad. It's going to spread the genome. Okay, so if it doesn't detect the knots, it's a dead end. If it doesn't, if it only cuts and doesn't reconnect, it's a dead end. If it can reconnect but it doesn't cut, it's a dead end. If it cuts and reconnects and detects but it doesn't entangle, it's a dead end. You need to have, it's kind of an all-in-one requirement. And
Yeah, that irreducible sophistication.
I like the word all or nothing core. All or nothing core requirements. Unfortunately, irreducible complexity has it's gotten to be such an abused term. I personally
No, yours is better. Yours is better. It's fewer syllables, which is more relatable to more people who've been educated in the government schools. All in one core.
all or
function.
nothing, all or nothing. The comeback by evolutionists, they'll just say, well, new genes arise all the time. I said, okay, let's grant that you get all these new genes. Do you have any of this level of complexity? And they'll say, well, it gradually evolved. I say, well, it's kind of hard to gradually evolve if the system's going to be dead if you don't have all in one. So
What's going on here is Sal is using different words to make the same argument. He's describing irreducibly complex systems. He's taking that concept and applying it specifically to de novo genes. The problem here is that this argument, irreducible complexity, has been refuted over and over again by many different people. This was like one of the central arguments in Kitzmiller v. Dover, the intelligent design trial. I've covered this on this channel multiple times, so I have a video specifically on irreducible complexity. I also interviewed Dr. Michael Behe on this channel on the topic of irreducible complexity. And here's the thing. I mentioned a minute ago that Sal doesn't like to use the term irreducible complexity. He doesn't like to make irreducible complexity arguments. The reason for that is that interview with Dr. Michael Behe. He doesn't think Behe did a good job defending that argument, and in light of that interview, he doesn't think it is a defensible argument to make. So what we see instead is he's making the same argument structurally, he's just using different words to do it. But at the end of the day, it is fundamentally an irreducible complexity argument. So in summary, Sal Cordova argues that gene families refute evolution. However, evidence shows that new genes evolve readily. It's a frequent thing, we can document it, and we can document the mechanism. Given that, Sal does not quantify the amount of new de novo genes or the complexity of new genes that cannot evolve. If we say, okay, a little bit can evolve, but a lot cannot, we don't know where that line is, and there's no effort to determine where that line is or if that line even exists. But at the end of the day, this is actually just an irreducible complexity argument. We're using different words to make the same long debunked irreducible complexity argument that is not fundamentally different from the argument Michael Behe was making in 1996. So, do protein orchards destroy evolution? No, they do not. That is a creation myth. Thank you all for watching. Please remember to do all of the algorithm-friendly things for this video. Hit the like button, leave a comment, share this video, and if you're not already subscribed to the channel, please become a subscriber. If you are subscribed and you really like what's going on here, please consider becoming a channel member. Channel members at any level get immediate access to my pre-recorded videos when I upload them, instead of having to wait for the public release date. Thank you especially to my second-tier members. There's more of you now than there used to be, so I'm not going to name all of you, but I appreciate your support. Thank you all again for watching, and as always, don't get fooled.